Okay, we're ready.
All right. So today we are having a quick discussion on the outcomes from the condenser design project with GE Vernova that you guys have all completed within the last week. So I'll just start with a refresher for 2 seconds on what we asked you to do, and then we'll get into some learnings. So hopefully you designed a condenser as the outcome of this design project. So as this probably looks familiar, we provided you with some process conditions and said, hey, can you figure out a heat exchanger to design that meets this criteria and that we can fit at the local GRU power plant? And we were hoping to receive a presentation from you that was a 5-minute pitch that told us what was your final design, how you got there, and some key considerations such as your footprint, costs, both operational and material costs. So, what we didn't discuss as part of the prompt, but were the lurking considerations, I actually meant to highlight much more of these variables, is that there are a lot of open-ended variables that you could consider when designing this problem. So I've pasted some of the equations to consider on the right-hand side, right? So your overall heat flow, it cares about your heat transfer coefficient, your heat exchanger area, your flow rate, your LMTD. Your LMTD cares about your outlet temperature, which we did not specify. Um, then we also ask for operational costs, which are linked to your pressure drop, right? So your pressure drop is linked to your geometry. So that I have here the pressure drop equation. So your geometry defines your velocity and some of your loss coefficients. So the question to ask is, as you approach this design problem, first of all, did you identify these variables? Um, and hopefully you did. I think most of you did because we saw some pretty robust calculations that came out of this project. But with this being a open-ended project with a week's worth of time to complete, it was likely impossible for you to evaluate every single one of these variables. You had to choose some that you said, okay, we're going to make informed decisions based on available data and just use those as fixed values. And others you evaluated, whether that was iteratively or doing some general research. So I'd be curious as you reflect on this project, how you approach the problem. Did you identify these key variables and how did you determine what was most important to solve and what to assume? So all that's just a little precursor, but I wanted to give some general highlights. So thank you to the two groups that were brave enough to come and present live on Tuesday. Beyond that, I did watch a couple more of the presentations online. So I was very grateful for everybody's dedication to putting those together. Generally, I was very impressed with the robustness of the presentations, the breadth that students went, but also the depth. So I think that's highlight number one for me is, as I said, the goal was to keep this general, to put you in the shoes of a real engineer who's given a generic problem and you have to bound it yourself and find a solution. So I was very happy to see some of the considerations that different groups brought in and evaluated, even beyond the more general measures that I brought. So I said, hey, you need to reject a certain thermal duty. Here's some boundaries. But you guys identified that there's more considerations to a design than just your thermal duty and your footprint and cost, such as maintenance. This is a plant in the middle of the city, so you have to care about the level of sound. I heard a few groups talk about that. Corrosion of the materials you select. So this being a heat transfer class, it's very easy to say, okay, here's a material that's highly conductive. It has like a high specific heat. Perfect. I'm going to run with this. So I was very happy to hear students talk not just about the heat transfer view of a material, but also the overall maintainability of their selections. A second thing I was very happy to see was, of course, you had to do calculations, right? That's the key part of this, is to size your condenser. But a lot of groups, what I was really hoping they would do, which is to say, okay, this is not a first of a kind design. There are hundreds, if not thousands, of condensers out in the world, and there's data available. So I was impressed to see different checks on thermal duty, footprint, cost, to make sure that the outcomes that you did were reasonable. That's something that I have to do all the time in my daily job. If I'm designing something new for the first time and there's no precedent within GE, I need to figure out somehow if what I'm getting is correct. And level one is saying, okay, let me check my inputs, make sure those make sense. Let me check my equations, make sure those make sense. And both of those I can do internally with other experts. But the third is to say, okay, there's precedent out in the world. Let's check against those and see if what I'm doing gives me an order of magnitude to make sense. So there were some examples of that that I thought were really great. I think on the flip, there is a consideration there for groups that maybe didn't do that. When you got your overall footprint, for example, I think I saw one group where their footprint for their ACC was less than the existing the cooling tower on site. We generically know that the specific heat of water is much greater than air. So that should have been a little red flag to say, hey, if I'm getting an air-cooled condenser that is smaller than an existing water condenser, maybe check my equations. One more example that I'll give that I gave to the live group is on cost. So I saw some operation costs that were $2 million a year. Considering the size of the plant, when you get to that outcome, we know that the purpose of this plant is to produce power and to make money, right? So one check that I didn't see anyone do that I would have loved to see is to say, okay, we know based on public data, the power output in kilowatts or megawatts from this plant. How does my power consumption stack up against that? How much am I eating into the overall efficiency? And or that can be converted because I did give operating hours per year, or you can find public data on the runtime of the plant. You could actually estimate the total kilowatt hours per year from the plant. And most teams did calculate your kilowatt hours consumption, so you can give that as a little gut check. Does the design I'm proposing make sense, or am I consuming 30% of the power? So, little tidbit, I think a lot of groups got at least partially there, which for it being the first time solving this problem and having a week, I was quite happy with. I think another highlight was iteration. Some groups did this, some groups did not. For an open-ended problem like this, one key element we were hoping to see you get to was that you can't just pick a design, go with it, and give the solution. You have to consider different options. So I gave you the open-ended prompt of you need to consider water versus air. Most of the groups I saw picked one as a starting point and only evaluated that. I do need to give a shout out. I think it was group 5 that actually did calculations on both water and air so that they could have a numerical reasoning. So I think that was a really great approach. Something you might do in real life execution is say, I'm going to use a lot more assumptions and do a quick and dirty calculation of both, get a guiding answer, and then go down one level and say, okay, I did some quick math. This one looks better. Now I'm going to start with that one and go one level deeper and get a more robust design. So I was very happy with group 5, for instance, on comparing water versus air. And then other groups compared a variety of approach temperatures to see that relationship with performance. Others evaluated different flows. So that was a really great process and what I was hoping to see. So thank you very much for doing that. I'm already starting to get tired of the sound of my own voice, but let's consideration. So I think I peppered some in with the highlights here. But one question that popped in my head a lot when I was listening to presentations is, did you consider where your site is at? When it came to the air-cooled condenser proposition specifically, there were a lot of claims that the decision to air-cooled condenser was because there was zero water consumption. Does that matter in Gainesville, Florida? We have an aquifer, there's water available. So I think one level deeper of why should be given when you say, okay, this is a theoretically zero water sounds like a good thing. But when you're trading that off with other variables, you need to tell me why this is important for our specific site. Another one on the flip, balancing between the highlight and low light, is I heard a lot of comments acknowledging that sound is important if you're doing the air-cooled condenser for the fan. I was very glad that people thought of that. But what I didn't see is anyone actually checking. So I think the general requirements for facilities is around like 85 decibels. Being in the middle of the city, it might be different. So I think that if you're doing this in the future, that could have been a great quick and dirty check to say, is it even allowable for me to install 5, 10 giant fans that I'm proposing within the middle of the city? Um, so yeah, one little tidbit, but I do have to give kudos for the fact people did mention sound, so it was definitely on their mind, even if they didn't know how to check the actual decibels. Another one is going back to assumptions. I mentioned this previously, I'll probably mention it again in a few minutes, is as I said before, you have to make some assumptions in order to complete this project within a week. Um, but comment on how those assumptions affected your outcome and the potential magnitude that it can affect your outcome, right? So as I'm going through the design process in my day-to-day job, there's a lot of unknowns that I haven't had the chance to validate in the current project that I'm working on. And that is okay, but I need to tell my management, hey, I haven't defined my flow rate or I've assumed a flow rate, and that assumption might be plus or minus 20% correct. So that's something to consider as you're laying out what you do assume, what you don't assume. How does that affect your overall outcome and proposition? And I think finally, if you're making a claim, back it up with data reasoning. I think for the most part, groups were very good about this. But I think even with the example I just gave, right? If you're assuming a 10 millimeter tube diameter, if you're assuming that water cooled condensers are more efficient than air cooled condensers, either do the math and prove it to me or tell me the foundations of where that came from. So that's my highlight reel from the student presentations. Like I said, otherwise I was quite happy with what everyone did. So now I'll go into, go
Can
ahead.
I just to pause for a second and maybe
Yeah,
break up the so just maybe one or two questions.
yeah,
So first one is I got to watch all 33 of these.
yeah.
And it gets we had the same thing with Sandvik. The Sandvik engineers are like, you actually sit for 5 straight hours and watch every single one. I'm like, yes,
Hmm.
because you have to be able to compare them to each other. Um,
Yeah.
so I ended up seeing, basically almost the same thing over and over and over again. There were a couple of
Hmm.
groups that did like a hybrid where there was a little bit of air and a little bit of wet tower. But
Mm.
for the most part, they picked one or the other and just went with it. And so it was like, basically 33 versions of the same or similar. Um,
Yeah.
is there so we encounter this in 4502 all the time, right? It's and there's actually now like an internet personality, a talking head, Rory Sunderland is his name, who talks a lot about like the value of taking risks in innovation. um
Hmm.
it, Probably, very likely, given that we know, exactly what has already been built at this facility, water tower plus heat exchanger or maybe air cooled is probably the right answer. But
Hmm.
is there value from an industry perspective in students or not engineers in practice
Hmm.
proposing ideas that are like outside the box? And the my specific question is there was one group that I was almost going to do it. So most of the groups when they did like the satellite view, they gave me just a satellite view of the Kelly plant and none of the stuff around it. And there was
Hmm.
one group that gave me a view of the Kelly plant plus Depot Park, which is south of it. And
Hmm.
Depot Park has a huge man-made lake, like a huge artificial lake in it. And what I
Hmm.
thought they were going to do, I was so excited. I'm like, these guys are going to use the Depot Park Lake as a cooling reservoir for their power plant. That's awesome. And then they immediately were like, we're not going to do that because Depot Park is there. We don't want to like,
Yeah.
burrow under the. I was so excited for about 15 seconds. Then I'm like, they showed me Depot Park to show me that they can't actually like expand southward. Um, and I have no idea whether that, lake is, big enough for the cooling needs of the
Mm,
plant,
hmm.
or whether I'm sure in fact, we've been there. There's like turtles and fish and stuff in it. So you'd have all those same kind of environmental problems that you have discharging water to a natural river or lake, and all the issues with permitting. But would you as an engineer evaluating all of the possible designs find value in a something that's out of the box? Like if you saw like 30 of the same thing, and then one engineer came in and was like, I want to like, basically pull water out of the Depot Park Lake and use that as my cooling reservoir. Like, does that have any value, or is it better, safer to just go with like a solution that is going to work?
I think that's a good question, and it depends on the needs of the customer, right? Like, I think the general happy engineering answer is you should always think outside of the box, but you also need to first define your CTQs, right? So if I'm like a power plant engineer and I have a repeat customer and I need to make a performance guarantee that's plus or minus a quarter of a percent, then I might say, okay, for this, I have to weigh the risk reward of whatever benefits I get of the out of the box design versus the reliability that I've already demonstrated. On the flip, right now, I am less in that space and more on the new technology introduction side. And if I think mainly inside the box of what we're already doing, then I am tripping over myself and preventing us from increasing our ceiling of what's possible. So if you have like one specific technology that you're working in, there's some specific ceiling of like, I mean, the equivalent would be like Carnot efficiency. You can't be more efficient than that. But if you choose a different process cycle, then okay, that, well, I guess Carnot efficiency is a bad example. But let's just say you have different capabilities per technology. The ceiling is going to be different for each one. So if someone comes out of left field and has this wackadoodle design, we might not say, okay, let's spend $10 million and introduce 30% more risk to do this. Maybe we do, or maybe that gives you inspiration of how to think outside of the box that you're already thinking and introduce new ideas piece by piece. So I see that all the time in my day-to-day job of people come up with crazy ideas, but we heavily incentivize people saying them out loud because even if you don't take it 100% of the way, it's inspiring you to see, okay, what good tidbits of that can I grab and add to this good thing that I'm already doing? So I think for the example you said, I was kind of hoping if somebody proposed an ACC, I knew the footprint would be big. I was hoping someone would say, okay, like this is what's next door. It would cost probably $1 million to wipe out the bus stop and replace it with an air cooled condenser. Why don't we do that? This is why we think it's better. Um,
Yeah.
yeah.
Yeah. So next, it's actually the fire department is next door.
Oh,
Uh,
okay. Maybe not
yeah.
get rid of that.
Well, but so interestingly, when we were at the Deerhaven generating station, and Deerhaven's a different power plant, right? But it's all the same engineers. They
Hmm.
move back and forth between the two power plants. Apparently, the engineer, the guy's name was Eric. He was telling us GRU evaluated the possibility
Mm.
of actually putting an ACC into the downtown Kelly station, and they were told that they could not like bulldoze the fire station, and they
Mm.
also could
Fair.
not move their they have a chunk of land to the I gotta think about what direction to the east that's GRU controlled land, but it's they would have had to put the steam like conduit through their transformer switching station. And
Hmm.
what Eric said is he's like, yeah, we evaluated the cost and came to the conclusion that we could build an entirely new power plant for the cost that it would take to basically move the transformers and rewire everything and like basically get everything out of the way so that we could move the steam conduit like through that parcel of land. And then also over Sweet Branch, I think it's called Sweet Branch Creek. They would also
Hmm.
have also had to go over the creek. And so he's like, yeah, it was just too expensive to do ACC because of the footprint required and like the guidance from the city that we could not bulldoze the fire station. And so we had to go even further to the east to GRU controlled land.
Yeah.
Um, so, but yeah, I was also surprised that nobody like even suggested it, that nobody thought about that. They were constrained by like the postage stamp that the current power plant sits on. So um,
Yeah.
yeah, the other so while we're talking about like crazy out of the box ideas, and I mean you guys must face this all the time. Um, like it's humid, right? It's like horribly humid, and they're like like why are we doing like these wet cooling towers in like this just kills me about UF too. UF has wet cooling towers all over the place, and
Mm-hmm.
they're running like full bore all summer because the humidity
Mm-hmm.
is like 95%, right? There's
Right.
very little extra capacity in the air to absorb more water per the psychrometric chart. um is there some other like crazy like I kept thinking to myself, like maybe you could like heat up the air in advance, right? Like use the effluent from the turbine to like heat up the
Mm,
air and somehow run it through, and like or use like some sort of dehumidification wheel or something like that to
yeah.
dehumidify the air before you run it through, just because it's so humid in Florida. um those wet cooling towers are all, I mean, they're not almost useless. They obviously, dissipate megawatts of thermal power, but still they're
Mm-hmm.
they're much less effective than they would be in a dry climate. Like my parents live in Las Vegas, and my dad is constantly reminding me it's 120 Fahrenheit here, but it's a dry heat, right? I'm like, yeah,
Yeah.
it's 90 Fahrenheit here with 90% relative humidity. I'm hotter than you are, Dad. So so kind of a similar question, but instead of like thinking about like geometry, like how do
Mm-hmm.
you guys deal with, like, you've got all these technologies that work great, that are sort of the textbook technologies that work great in the Northeast, right, or the desert,
Mm-hmm.
but they don't work so well in hot humid environments. Like how do you, like, does anybody ever say like what are we doing, right? It's like, why don't we come up with something that's specifically designed for this humid climate?
I wish I had a good answer to that. I'm like a bit out of touch in like any of the power plant designs I've done have been either uh wet cooling tower or ACC. So
Yeah.
I personally haven't seen any out of the box thinking. But that doesn't mean it's not there. I mean, you could I like a wet cooling tower, I think I was Googling right before this, is about a standard one is about like 30% convection and like 70% latent heat. So you could say, okay, I'm going to do the same thing as an air cooled condenser and be only convection. But I wonder if the thought is even if you're only 10 or 20% um, latent heat, like in a very humid climate, maybe that's worth it just because that's so much more power dense than the equivalent like airflow needed for convection.
Yeah, yeah, it's possible. I don't know.
But I
The
don't
other
know.
thing, the other thing that occurred to me is, and I don't. This would probably be it's a whole separate kind of thermal pollution, but a big deal in Gainesville now is, at least at the residential scale, is heat pumps. So
Mm-hmm.
instead of pure air conditioning, using a heat pump, and particularly using the ground as your
Yeah.
thermal sink. And I realized that like over time, and plus it's expensive to drill those boreholes. We could actually get Sandvik to drill the boreholes, and then you guys could like put your heat exchanger down into the ground. Over time, the ground would obviously heat up, and that's I think a problem with like large scale heat dissipation into the ground. But yeah, it's as I was watching all those videos, I was like, man, like this is neither one of these solutions is particularly great for
Yeah.
Florida, and yet there's nothing else, right? Nobody else has come
Yeah.
up with like the killer app for how you
Mm-hmm.
dissipate heat in a hot, humid, Florida environment. So anyway, sorry to like railroad and but I just like all those things came to mind as I was like watching the presentations.
Mm-hmm. And I think that I just to give like the softer tidbit of like going into your day-to-day job as people go into internships or graduate is when especially being early career, I'm still early-ish career. At first, I would be nervous if I had crazy ideas or had the thought of like, oh, why do they do it this way? Why don't they do it this really wacky way? Um, I initially was scared to ask those things because I assumed, like, GE Vernova, for instance, has been around for 100 years. I think these people know what they're talking about, right?
Yeah.
So it made me scared to even ask the question or vocalize my opinion. But innovation is happening all the time. 100 years in the span of like the lifetime of humanity is still relatively short. Like the Industrial Revolution was not that long ago. All that to say, like your ideas can make an impact, and especially when you're an old company like GE, you need those fresh ideas. You need those hard questions to say, oh, I hadn't thought about it before. I forgot that I made X assumption 10 years ago, and we've just ridden with it since. And
Yeah.
actually, we evaluated that. Maybe there is this lever that we can do better. Um, so that's the value of exercises like these is it's so easy to iterate on something existing. It is a lot harder to get outside of that starting bound.
Yeah. Yeah. No, yeah. The students did exactly what we asked them to do. So I'm not
Yeah.
complaining, but I just, especially teaching 4502, right? Where that sort of out of the box thinking and innovation is rewarded.
Hmm.
I don't want to use the word disappointed because that's not like they did exactly what we asked them to do. I was, I don't have the word, but just, I was hoping somebody would come up with something just crazy. And even if it didn't work,
Yeah.
would go through the process of like, we're going to put all that thermal energy into a laser and shoot it out into space or something. I don't know, something crazy. And it just, nobody did that. So I was just a little sad. But
Yeah.
anyway, but good to have like an industry perspective of like whether that kind of out of the box thinking is valuable. I mean, I hear you that it's, um, you know, every the company's been around 100 plus years. They know what they're doing, but then there also is, and this happens in academia too, that, we've always done it this way. It works. So let's just keep doing it this way kind of mindset.
Hmm.
And so somehow those have to balance. I mentioned Rory Sutherland, who talks about Rory Sunderland, who talks about, like creative thinking. And one of the points that he makes, which I think is very good, is if you choose the thing that everybody expects you to choose, you're not going to get fired, right? Even if it's not
Yeah.
the best solution, because everybody just expects that to be the answer.
Hmm.
So, and then you mentioned as a junior engineer coming in and not wanting to say something silly, um, because there definitely is that risk, right? Of you're sitting in the conference room and you're like, let's do this crazy thing, and everybody's like, what? So, but then at the same time, if nobody challenges assumptions, then progress doesn't get made. So,
Right.
yeah.
Absolutely.
Anyway, sorry to interrupt you, but so
Yeah,
carry
no
on.
worries. I think I'd probably take 5 minutes and go through these last overall recommendations. So I think what I started with, I also want to end it with like the assumptions that you make are the most important to your overall outcome. And one thing I saw in presentations a lot was there would be an assumption slide, but it was very much the same assumptions that you might receive in a bulleted list at the start of a textbook problem, right? I'm assuming this is steady state. I'm assuming my pressure is fixed. I'm assuming a constant CP. But then as you went through your analysis, you would say, I assumed that my fin pitch is going to be X. I picked a diameter of 20 millimeters, but didn't actually acknowledge those as assumptions. But those drive your overall outcome, and those influence how your outcome would change. So that's my recommendation going forward. Of if this was a real design review, if I was taking this at my job, then we spend the most time when we're in front of a chief engineer on the first couple slides of any design review to say, okay, this is my assumptions. This is why it's valid that I use these assumptions, or this is the risk that I'm introducing by assuming those things. So I know I'm beating on that one, but I think that is super duper important if you forget everything else. Um, and the second bullet point here is the exact emphasizing the same thing. This is an open-ended problem, so I didn't expect you to be able to define everything within a week. But you need to come to me when you're presenting and say, this is what I chose to define and this is what I didn't. But I'll stop there since I've waxed on about that. The third one is, and this is a lighter one, but I heard a few different groups as they introduced their calculations say, hey, I used Cantera, I used MATLAB, I used some automation tool for this calculation. You can provide that, but that is not equal to the methodology used. That is a tool only. It is not a philosophy. It is not physics. So it is fine to say I used MATLAB. Here's the equations that I put in MATLAB, or I used this steady state software, but you have to give what went into it because that is the foundation of what's calculating, not the tool itself. The fourth one is open with your criteria for success. This is also just like design review tip, right? As I said at the start, I gave you some explicit criteria, such as you need to use this mass flow, you need to reject this amount of energy. But there's other criteria that, of course, you guys had in your heads as you designed this. Of this needs to be relatively cheap. This needs to last a certain amount of time before it falls apart. This needs to not enrage the people of Gainesville. So as you're proposing a design, you should define at the very beginning, this is what I'm trying to achieve. And even as you're going through your design process, do that at the start with your team and then check yourself against those, we call them CTQs, critical to quality. Check what you're doing and where you're at in the process against what you've defined as your criteria. And then last recommendation is AI is a great tool, but like I can see sometimes it's obvious where you're using it. And in some places that's great. It makes for beautiful presentations very quickly. It's great to bounce off ideas. I use AI all the time of, I am an engineer designing a pump. What should I consider? It's good. So in industry, we are using AI all the time. We're learning the different ways that we can embrace it. But A, it's only as strong as its inputs, and B, it is not an engineer, you are. So it should not be solving the problem for you. It should be an assistant. You can use it for guiding, brainstorming. And in some places, I think there were presentations I saw where you might have used it and it wasn't obvious. But unfortunately, there were some presentations where it was clearly used and not in an effective way, where the team didn't necessarily do the clear thinking first to understand the problem before they interacted with AI for assistance. So that's where I say it's only as strong as its inputs. If you don't understand the problems, you don't understand the bounds, then you're setting yourself up for a high amount of risk of getting an incomplete outcome that you don't know how to assess if it's complete. So that is my feedback for you. My takeaways from this week were that you can accomplish a lot in a week. So I gave a very open-ended question and I didn't know what the results would be since this is the first time we're doing this, but I was wildly impressed with the presentations and all the different avenues that students went down. I think one group even did ANSYS. I was very much not expecting that, but very impressed. And second, you are capable of dealing with these problems and developing robust solutions. As I said, I presented you an open-ended problem and let you figure out what I wanted, but I wasn't sure how far you would take it. But I think like the key pillars that I was looking for the most part, you sniffed those out and started to talk to them. So I'm very pleased and think you'll be great in the workforce. And then my final one is 5 minutes is short. I realize now that we asked for a lot of work from you, and watching those presentations, my hair was like blowing back because everyone's talking so fast to get all the content through. So all that to say, I acknowledge that we asked for a lot of work of you and that the 5 minute presentations was probably a bit of a squeeze to convey all that you did. So that was one of my quick lessons learned. And then finally, I am going to give a plug. I think some students were ambitious and already found me on LinkedIn. So thank you for that. GE will be on campus this fall at Career Showcase. So please talk to us. We hire for interns and for full-time, have cool rotational programs, blah, 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 blah. So feel free to check out our careers page. And like I said, if you reach out to me on LinkedIn, the thing I will tell you, if you ask how to connect with GE, is connect with us when we're on campus. That's the most effective way. We're at Showcase, we're usually at Shep's, We Barbecue, we're all over the place during that week. So there will be plenty of time to connect with us in person and give it your best shot. But our goal of this activity, I guess the last thing I'll say, is for us to hopefully get you more excited about the energy industry and maybe even GE Vernova. And on the flip, for you to give you a little bit better of a taste of the kind of problems you might solve in industry and hopefully make heat transfer feel a little bit more real. So I think Dr. Thomas sent out a survey for you. So think about those. That's the mission of what I'm trying to achieve. If you think, man, you really crashed and burned and did not achieve that, let us know. Hopefully that's not the case, or if it did really work. Either way, we would really appreciate that feedback so that we can continue to make things better. Hoorah. That's my, that's it.
Whoa, thank you. Um, we still have the two students that were here
Yes.
when we started. So if do you guys have any questions, comments, and like I said, you can just ask them, or if you want to just drop them in chat, I can read them if you don't want to be recorded. Maybe not. Oh, yes. Oh, just thank you. This was great.
Thanks, Anna.
Yeah.
All right.
Yeah. Okay. I think we're good to go then. I of course have tons more questions, but I want to respect everybody's time. Okay. Um, so another comment. Thank you. I feel like I learned a lot from this. Thank you. We appreciate that.
Yay.
Yeah, my questions are all around AI and how
Mm.
that's impacting you guys and the energy. Whoa, oh, there we go. Sorry, I just had a little bit of a brownout. Wow. Okay, but
Oh,
I'm still here. I'm still stable.
yeah.
Um, so yeah, we can have the AI chat later. Um, but yeah, I was this is like just it's like killing the university. So there's some
Do we want
faculty.
to keep the recording?
I mean, yeah, we
Yeah.
probably can. Yeah, I mean, this is it's there's nothing that I would say that wouldn't be. It's so some faculty are just like, no, you cannot use AI. If I see you using AI, you fail my class. They're just
Mm-hmm.
banning it outright.
Mm-hmm.
Um, my approach is use it. In fact, you're encouraged to use it because, as you said, this is the real world, right? Is
Yeah.
engineers are using it like all the time, and so our students have to know like the basics of how to use AI when they go out into the world. Um, but the challenge is the entire curriculum is set up for like a pre-AI world.
Mm-hmm.
And like for example, I'll give them I know they do this. I'll give them the homework problems, which are graded, and I, I just drop them into the AI and it gives them
Mm-hmm.
the answers. And I have the perfect homework scores across the board, right? I mean, I guess to be fair, I do eventually release the solutions to them. So if students, are patient long enough, they do get the solutions. So probably some of them get perfect scores from that. But sometimes I'll release the homework and within like 3 minutes, like 12 students have submitted the answers. And it's like,
Mm-hmm.
whoa, okay, that was definitely um and then they get I'll use the word cranky. They get cranky when you ask them harder questions. They want to use AI to solve problems that were created in a time before AI, and they get
Mm-hmm.
upset if you give them something harder,
Mm-hmm.
which is intentionally designed for AI. So this is something that's like we're still navigating like where the sweet spot is. Um, but I appreciate that you pointed that out because I saw the same thing, right? There were instances where, um, in all the not all the but in many of the presentations, um, where it was clear that they, they used AI to generate like images and scripts, and you could see them like
Mm-hmm.
reading off of the scripts. Um, and it's like when I solve, so like for example, I just released the solutions to one of the quizzes that I put out in the class, which was a post AI quiz, in that it was really hard.
Mm-hmm.
And in fact, when I fed it into AI, the AI got it wrong.
Mm.
Um, but I will actually sit with like one AI window open, and then I'm old, so I'll have like Excel sitting open on the other
Yeah.
window, and I'll actually go like step by step by step through, and make sure that everything that I'm doing in Excel is mirrored by the AI, And if there
Yeah.
and sometimes like yesterday, like it's very good at catching mistakes. So I input the wrong thermal conductivity for one of the metals that I was using in a fin.
Mm-hmm.
And it caught my mistake. So that was awesome, right? That saved, tons and tons of drama and hardship on my part,
Mm-hmm.
posting a solution that's wrong. Um, so it's a great tool for like, checking your work. And like the other, like I have no idea how to solve like what is it? For the temperature profile on a flat plate with like weird boundary conditions. I can
Yeah.
do it like separation of variables. That's what it's called. I can do it for just a normal flat plate, but when you start adding like weird boundaries, like
Mm-hmm.
that requires a math PhD. I don't know how to do that, but
Yeah.
AI can do it, right?
Mm-hmm.
But you cannot trust what it says. You actually have to go through and do the steps yourself and believe and understand like every single step. And I
Yeah.
saw in a couple of cases, not with your project, but with this quiz, um, a couple of cases where the students very clearly just like got the equation from AI and didn't actually check it, and then they used it incorrectly. Um,
Mm-hmm.
so I'm interested in your opinion. Um, like like how does industry view AI, and like where is that going, and what are the pitfalls of over reliance on it?
Yeah, and I think it's still very like you asked me, I would give you a different answer than my boss is a different answer than his boss. But the thing I think about fun, like it is a useful tool. At the same time, like a large language model does not know physics.
Yeah,
So as an engine, like that is, I think, the guiding principle that is easy to remember to help be a judgment of like, should I use AI here? Should I not? So for me, like I said, like it has saved me a bunch of time. It has saved my technical leader, which is like a technical mentor, a lot of time of stupid questions that the internet can answer that I now don't have to ask the person beside of me. But it never should be my final source of truth. So I use it a lot to like start brainstorming of like, how should I approach this problem? Or I'm 5 years rusty on taking an undergrad heat transfer course, and now I'm having to like in my day to day, I've been solving like a heat transfer conduction equation and I'm rusty on that. So like having those conversations makes me remember, oh, I remember this transient, blah, 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 blah. But I don't use like anything I use, especially computationally, has to be something that I understand enough that I can check it. I'm
yeah,
never going to give, like, as I said, fundamentally, AI is not, cannot do physics. It is predicting what you can say. And it's getting better and better and better at it, but it is still non computational. So you are responsible for checking the assumptions, which was the main thing I talked about before, and checking the philosophy that it's using. But I think it saves a lot of time and like some of the like for like the heat transfer example, like it saved me a lot of time to be like, hey, this is exactly what I'm trying to achieve. And it's like, okay, here's a reminder of your fundamental equations. That's a lot quicker than me grabbing a textbook and flipping page by page by page until I'm like, oh yeah, HA delta T. I remember. Um, or automation, right? Like when I mentioned presentations, the doing stuff of like making it pretty, if Copilot can make your slides gorgeous and all you have to do is put in some notes, that's a win for everybody. Or I think like another example I would use is when I'm trying to plot something or automate a computation, I might use Claude to say, hey, like here's this generally what I'm doing. Can you write me a code so that I can process this data quicker? So like having it, I've used Claude to write me code to like plot different data that I'm processing. But the fundamentals of like how I'm processing the data, like I need to know. I'm like, I have to be able to present to someone to say, like, if I'm integrating the thermal heat here and I'm assuming XYZ losses, this is what's happening. Like, it is not robust enough that I can say, like, oh, hello, Mr. Chief Engineer. Claude said that this is the
yeah,
answer.
yeah,
So,
yeah. Okay, that's a good. Yeah, no, I had that moment last night as I was working on a solution. I had AI. So we're some it's an exact solution to 2D conduction with transient. So it's a sum of a sum. It's a brutal equation.
Mm-hmm.
And I had AI generate it like a MATLAB code, and I could not figure out what the code was doing. I'm like,
Mm-hmm.
I do not understand this. And so finally I just gave up, and I'm like, I'm gonna just,
Yeah.
go back to what I know. And like I said, I'm old. I programmed the whole thing in Excel, and it worked. And
Yeah.
it was ugly. It was like pages and pages and pages of spreadsheet, but I knew exactly what every cell was doing, and I could explain it to
Mm-hmm.
somebody else if I needed to.
Mm-hmm.
And yeah, so I think that is I think our students are missing that aspect of thinking of AI as a tool. It's I think they go too far. They um, ask it for something, it gives them the answer, and they don't think to go back and check in a way that, like, I love your criteria is great. The can I as the engineer explain this to my boss, right?
Mm-hmm.
Like if you can explain it to your boss, then go ahead and you're good. But
Mm-hmm.
if the AI generates something that you yourself could not explain, I think it's probably very dangerous to use it.
Right. And you can even like ask it to, like I've written code, didn't understand what I was doing and said, okay, explain to me what you did here. And then like I've had instances where I'm like, oh, that is not what I want you to do. I disagree, and then iterate with the AI to get it to do what I wanted it to.
Yeah,
So like there's different levels you could take it, but engineering as a whole, it's like when you're in university, you are learning tools in a toolkit. So you don't like I don't need to have memorized every single heat transfer equation or thermodynamics or fluids equation that I ever learned, but I more generically have walked away with how to approach different problems. And that's the point of like doing all these problems in university is to exercise those skills so when you're presented with a new problem, you know how to tackle it. So I think
yeah,
like the risk of AI is similar to the risk of cheating in university, right? Is if you're not actually doing those exercises, when you get to a point that like AI can't do the job for you, which you wouldn't have a job if AI could do everything for you, then do you know how to exercise the toolkit that you've built to solve it?
yeah, yeah, yeah.
So,
That's good. Well, it's interesting that you make, it's not a perfect analogy, but you make the analogy to cheating. There's a ton of literature, tons about the long-term consequences, not to institutions, but to individuals
mm-hmm,
who cheat. And it's actually been quantified. It's hundreds of thousands of dollars in income that you're
mm-hmm,
basically giving up by cheating because, as you said, there's a set of skills that you're missing. And when you get onto the real world and you don't have those skills, you like miss opportunities for advancement.
mm-hmm.
And it's actually been quantified. So interesting.
Yeah. To me, it's
Anyway,
a similar moral, like, because to be transparent, like when I was in school, there, you're rewriting version, like people have historical answers on tests and
yeah,
homeworks, and some professors, it's like, you know, that 100% of the solutions are available online. And like, I had to make the moral choice of like, hey, I know that I could use this, but like, it's not going to benefit me long term. And so I think students now just have it's one level more accessible than maybe it was for me when it was like cheating, which is also a dirtier word than using AI. But I think the temptation has always been there one way or another, and students just have to choose for themselves to do the harder thing in order to get what they're paying for from the learning experience.
yeah, yeah. We went to I think I mentioned this to you in a previous conversation. We went to Boston, Massachusetts, my wife and I, my kids. That was our 20-year like wedding anniversary. So we went back to,
Mm,
the church we got married in and stuff. But we made a stop, of course, at MIT. And we my wife's advisor is still there. So Monty Krieger is the guy's name. He's about to retire. He's if I had to guess, I would put him in his mid to late 70s now. So he's kind of in the twilight of his active career. But he made the exact same point, and I thought, wow, what a how much wisdom! Like it's amazing. He's like, why would you come to like MIT or like UF in this context, or Georgia Tech for you? And like not avail yourself of like the learning opportunity, right? You
mm-hmm,
come and you're just gonna like AI or cheat your way through. Like, what are you actually like paid for, right? What are you getting out of
mm-hmm,
that whole? Maybe you get like the credential, the piece of paper, but there's nothing backing it up, and that lack of expertise and knowledge and skills and experience is going to make itself known when you get out into the world and you're tested for real.
Mm-hmm.
So yeah, I mean it's this is so this guy's like he's been teaching for probably 50, 60 years. No, not 60. That would make he started teaching at 12, but probably 50 years, right? Because
Yeah.
started his career probably, mid 20s. Um and even he had that realization and is realizing like, how like like the value of going through the struggle um is the struggle itself. It's not the answers that you get, it's the struggle. And
Right.
that's what like the university continues to provide, even in a world where the answers are readily available.
Mm-hmm.
And I think some students at least are losing sight of that, and they just fixate on getting the answer so they can move on to the next thing. So anyway, who knows? This is the beginning of a whole new paradigm in like education. So we'll
Mm-hmm.
see how it goes and who wins in the end. I'm not sure.
That's right.
Anyway, we're coming up on an hour, and we said half an hour.
Yes.
So sorry for sucking up your whole afternoon with this, but
No worries.
anyway, want to just thank you again officially, since we're still recording, for doing all this and the time that you spent and watching the videos and interacting with the students and coming up with a really cool, like, I think just very appropriately kind of weighted and structured problem. It was, I think, just right for the amount of time and the amount of expertise that the students had, and then making the connection with GRU. Like I said, I've been trying to get into that power plant for like the
Yeah.
past 8 years, and
That
they
was
just
awesome.
ignored me. And you dropped one email, and they're like, "Oh, you're from GE? Okay, like anybody
Yeah.
that you say is cool can show up at our power plant." And I'm like, "Wow." So yeah, I appreciate all of that, and I'm I'm at least, if it's up to me, we'll obviously continue doing this,
Yeah.
and expand on it. I'm out for the coming year on professional development leave, but when I come back, if they let me teach heat transfer again, or fluids again, or maybe thermo, God willing,
Yeah. Ooh.
we definitely, well, that's a whole different fight. Um, we should definitely keep doing this. So, because
Yeah.
I thought it was quite valuable.
Yeah. I thought it was fun, if nothing else. And hopefully
Yeah,
we'll hear that the students enjoyed it. So our
yeah,
sample
yeah,
size of 2 today said it was good. So I will take that as a
yeah.
win.
Yeah, we'll get more. We'll get more. They'll I'm sure hundreds, not hundreds, but at least 100 of them will fill out the survey. So we'll get good data from that.
Excellent.
Very good.
All
All right.
right. Well, happy Friday. Hopefully
Yeah,
enjoy your weekend.
I get to write a lab this weekend. That's my one final. They're going to do a convection lab. So um,
Ooh.
yeah, yeah, which I have to figure out how to do with like cups and straws and ice from the freezer, and like they've got these little lab kits that have almost nothing in them.
Mm-hmm.
So that's what I'll be doing. It's
It's
fun. I
fun.
have tons of fun, and my wife is like, "What are you doing?" You're like,
Mm-hmm.
watching ice melt. That's so boring. And I'm like, "This is the coolest thing ever!" Like, it's melting faster because we're blowing air on it. And she's like, "Oh my God!" So
Hey, I
anyway,
take it. That sounds pretty fun.
yeah, yeah, yeah. I have fun. So
Good.
anyway, cool. Well, we'll be in touch, and thanks for everything you've done.
All right. Thanks so much.
Yeah.
Bye.
Bye bye.